Let us now see how we can use the Java parallel fork join framework to get parallelism rather than the async finish API. So here again is a sequential array sum example that we had seen earlier. We happen to be computing the sum of reciprocals of an array, and interestingly, if x sub I is initialized to I, you end up getting the harmonic numbers. Now here's the parallel version using the fork join framework. And what we see is that we have to create the special object sum array, and we will take a look at that class. And then we have to invoke the object T using a fork join pool. And then when it's done, we get the answer, and then we can print the answer and also time the results. So what is this sum array class? Well, it's, as we had discussed earlier, it's something that extends recursive action, and the way tasks are specified using the fork join framework is by introducing your own class that subclasses recursive action or recursive task. And the key method here is compute. So in the async and finish API, we saw we could just provide a lambda that was the body of the computation. Here we have to put the computation in the special compute method. And what we will do is check the range that we want to do the computation for. This is going to be a recursive divide and conquer approach. And if the size of the range is below some threshold, we just do the work sequentially. Otherwise, we divide the array into two parts, left and right. We fork the computation of the left part. That is really like the async. And then while the left part is executing in parallel, we compute the right part, and then we do a join on the work in the left part of the array. After the join, we can get the answer from the left part of the array and the right and combine them. Now, what's really interesting about the fork join framework is it's a framework for recursive parallelism. So we have recursive calls to compute. Write.compute will recursively further subdivide the array until the size reaches a threshold, and left.fork in parallel creates a task to call the compute method on the left part of the array, and that too will be further subdivided. So let's see this what happens if we run this program. So we are getting the sequential version and the parallel version. They are producing the same answer, but something's not good. This parallel version is running slower than the sequential version. So we have to take a look and see what's going on. The sequential version is taking about 440 milliseconds. The parallel version is taking 620 milliseconds. Well, the sequential threshold plays a key role. The point is that there is an overhead in creating these tasks in any framework, whether it's fork, join, async, finish, and you want to make sure that there's enough work to justify that overhead. And we just had 5 additions as the threshold. That seems kind of low. We are doing the computation for 100 million elements, so we can go up to, let's say, 1,000 and still have lots of parallelism available. So let's try and run it again, now with a threshold of 1,000 instead of 5. And now we're getting what we had got with async finish. We see that the sequential version is again taking around 440 milliseconds, and the parallel version is taking about 220, 230 milliseconds. So that's good. We're getting two-way parallelism. But remember, here we are recursively subdividing. So my laptop happens to have 4 cores, and we should be able to get a better speed up than just a factor of 2. Well, what's going on? It turns out that there's a setting for the fork join pool which runs your parallel tasks, and that tells you the degree of parallelism you want to exploit. So here I had it originally set to 2. If I increase it to 4, let's see if that helps. So that means there will now be 4 worker threads in the fork join pool executing these tasks. And yes, indeed, we see we've gone from again 440 milliseconds in the sequential version to about 120 milliseconds in the parallel version. So by changing the setting to 4, we were able to use 4 cores, and depending on the kind of machine you run on, if you run on a server with 16 cores, you can use 16 and maybe get speed up close to a factor of 16. And this is exactly the principle that people use on larger computers to get programs to run 100,000 or even more times faster using parallel computing. So now you can get going with the standard Java framework for multi-core programming, the fork joint framework, and enjoy using it for the programs that you want to parallelize.